So we're jumping over section 4.2 for the moment. It'll make unit circles make more sense. And we're going to talk about 4.3 today. So 4.3 is right triangle trigonometry. Should be a walk down memory lane for you, because we're going to be talking about, first of all, SOHCAHTOA. Everybody remembers that, right? Okay. It's a mnemonic that helps us remember the proportions, or the fractions, the ratios of the sine, cosine, and tangent. So when we see SOHCAHTOA, we know that sine stands for, or the sine of an angle is equal to opposite over hypotenuse. And we like to abbreviate opposite with OPP, hypotenuse with HYP, so we don't have to write all of it out. Cosine is the ratio of what over what? Adjacent over hypotenuse. The A is for the adjacent, and the H is for the hypotenuse. And TOA, tangent, is the abbreviation for opposite over adjacent. Okay. So what is CSC? Cosecant. Cosecant, good. The cosecant is the hypotenuse over the opposite. It's the reciprocal of the sine. What does SEC stand for? The secant, because if the cosecant is one, secant is the other, it's the reciprocal of cosine. And what's cot? Cotangent. Some books do call it CTN. Okay, but our books calls it COT. Cotangent is the adjacent over the opposite. Okay. So when you see sine and cosine, does anybody have any idea what the co stands for? It's kind of reversed. Earlier we talked about, it's like it is together. Co typically means together, right? That's our prefix. But co is an abbreviation. Well, when we talked about comp and sup, right? What were those two? Complementary and supplementary, right? Okay. The co in cosine is the cofunction. It's the complementary. So that means that if we're talking about the sine, everybody know the sine of 30? What's the sine of 30? There's someone that said, I think. No. Sine of 30. Okay. Don't remember. That's okay. We got a lot of work to do. Sine of 30 is 1/2, right? Turns out that the cosine of 60 is also 1/2, because 30 and 60 are complementary angles. So the sine of 1 is equal to the cosine of its complement. Okay. So if I have if I knew the sine of 1 degree, I would know the cosine of 89 degrees. If I know the sine of 45, I also know the cosine of 45. Okay. Tangent and cotangent are complementary as well. So if I know the tangent of 45 degrees, I know the cotangent of 45 degrees. And if I know the tangent of 30 degrees, I know the cotangent of 60 degrees. Okay? So I can save you a lot on memorization. Likewise, the cosecant and the secant are complementary. So if I know the cosecant of 10 degrees, I know the secant of 80 degrees as well. Make sense? Cofunctions, complementary functions. Okay, so first hour we got into a discussion about where these words came from. I didn't remember where sine came from, and it's to do with abbreviations and so forth. And I won't go into a lot of detail with it, but tangent and secant do come from a circle with a tangent and a secant to the circle. And I don't want to spend a lot of time on this today because I want to keep moving. Okay, but if we have time at the end, we can go back if you're interested. All right, so next, we want to find the values of the 6 trig functions for this angle theta. Okay, so here's our angle. We know 4 is the, how is that related to the angle? Adjacent, and 2 is the opposite, so we don't know the hypotenuse. That's the first thing we have to do. We're going to use what? Pythagorean theorem. So we can find the tangent of this guy, but we can't find anything else. Well, tangent and cotangent. Can't find anything else until we use the Pythagorean theorem. So 4 squared, 2 squared is c squared. So square root of 20. You guys are quick. Everybody see how Justin got that? Okay, I don't want to lose anybody. 16 plus 4 gets us 20, so we have the square root of 20, and we have to take that perfect square out. We have to break it up. 4 comes out, and the 5 stays inside. Okay? All right, so we want the sine of theta now. So here's our theta. The sine is the SO, opposite of our hypotenuse. So we need to take the 2 over the 2 square roots of 5. I like that. We're just going to get 1 over the square root of 5. But can we leave it like that? No, because we don't like to have an irrational number in the denominator. So how do we rationalize that? Multiply it by square root of 5 in the denominator, square root of 5 in the numerator. So the square root of 5 times the square root of 5 is the square root of 25, which is 5 down there, which is good. That's what we're trying to get. And we get a square root of 5 on top. Okay? So if you remember how to simplify radicals and how to rationalize them as well. Okay? Cosine. The cos says to take the adjacent over the hypotenuse, so what will we get? 4 over 2 square roots of 5. So 4 and 2 cancel, and we'd have 2 over the square root of 5, which rationalizes to become good. You know the shortcut. It's like the radical goes up here and then disappears down below. 2 square roots of 5 over 5. You do enough of those, you see the pattern. Tangent, that's the TOA. Opposite and adjacent. Alex, what's it going to be? What's the tangent of theta? Good. And we simplify that to 1/2. Okay? We've done the heavy lifting now. All we have to do is find the reciprocals of these. But if you show your intermediate work, you don't have to go to this answer to find the reciprocal, because what's that going to do? Flip it and put a radical in the bottom, right? Isn't it better to flip this one? Okay, so we're just going to get the square root of 5 here. We're going to get the square root of 5 over 2 here. And we're going to get 2 over 1. Very good. Questions on this slide? Okay, next one. We're going to let theta be an acute angle such that the cosine of theta is 28/100. We need to find the sine and the tangent of theta. Caleb, what's going on? Okay, so we have an acute angle. Cosine of theta is 28/100. What does that mean? What's 28/100 in as a fraction? Exactly. So it make you pause and think for a moment, but that's 28 over 100. Can we reduce it to 14 over 50? You bet, because it doesn't matter how big those triangles are, right? They're all similar, so they're going to have proportional sizes. What would that also be? 7 over 25. Isn't that a nicer number to deal with than 28 over 100? Or, yeah, 28 over 100. So let's sketch out a triangle, okay? Some kind of triangle in which the adjacent is about 7 and the hypotenuse is about 25. So if this is my adjacent This is my hypotenuse. I'm supposed to find the sine of theta and the tangent of theta. So first step is what? Use the Pythagorean theorem. But this time we have the hypotenuse, right? So we don't say 7 squared plus 25 squared is something, right? It's 7 squared plus our b or a or whatever you want to call it is equal to, squared is equal to our 25 squared. Anybody recognize that Pythagorean triple? Nope. Okay. So 49 and b squared is 625, right? And so b squared will be 625 minus 49. And the square root, 24. We only want the positive value here because we don't want to talk about a negative length. Okay, so b is 24. That means that we're going to use the opposite and hypotenuse to find the sine, and the opposite and adjacent to find the tangent. So our heavy lifting's done. The sine of theta is what, Andrew? Perfect. And the tangent of theta is what, Brittany? Perfect. We're good on these? All right. So next example. We're going to let b be an acute angle such that the tangent of b is 4. It's actually a beta. Okay, so we had a theta before, we saw omega earlier, another one of those Greek and Latin alphabets. Okay, so this is our beta. And so someone said 4 what? Tangent of b is 4, right? So that means that's our TOA, 4 over 1. I like that. That helps us. So we are wanting an opposite to be 4 and our adjacent to be 1. So maybe something like this, where this is 1, this is 4, and there's our theta. Didn't really draw it to scale, but I tried. Okay. And we want to find the cotangent. Cotangent should be easy, right? What is it? Simply flip them, right? This is the reciprocal function for tangent. And now we just need to find the secant. Secant is the reciprocal for which one? Cosine. Okay, so we need the hypotenuse, right? Adjacent and hypotenuse. 1 squared, 4 squared, c squared, so 17, right? Square root of 17 can't really be rationalized, or they can't be simplified. It's as simple as it gets. So we want the hypotenuse over the adjacent, right? This is the reciprocal of cosine. So we want the hypotenuse over the adjacent. We're taking the square root of 17 and dividing it by 1. If you put the 1 in, if you don't put the 1 in, it doesn't matter to me. Questions on this one? All right, keep moving. We have a ramp at the top of a 3.5 foot dock, 3 5/10, 3.5. And it has to have an elevation of 12 degrees. We want to know how long will the ramp be. Okay, so we're looking for the hypotenuse. That's our x, our c, whatever you want to call it. So what parts do we have? Good. We have an opposite. We're looking for a hypotenuse, so we're using the sine of 12 degrees is equal to 3.5 feet over we don't know. Now, here's the key. Always, always, always solve for x first before you break out your calculator. Okay? Because most students are going to just start plugging numbers in. If we want to get the x by itself, it's in the denominator right now. What do? Cross multiply. So x times the sine of 12 is equal to 3.5 times 1. Okay? Or it's like multiplying both sides by x to make those guys disappear. Now, how do we get the x by itself? Good. So we want to take 3.5 and divide it by the sine of 12 degrees. So here's where we break out our calculator. So grab your graphing calculator. Nobody knows the sine of 30 degrees off the top of their head? 1/2. Good. Okay, it's 1/2. So on your calculator, I want you to press sine and 30 and see if you get 0.5. If you get 0.5 on the scientific on the graphing calculators, you didn't get 0.5, right? If you didn't, it's because you're not in the right mode. So anytime that you're taking a sine, cosine, or tangent of some measure, you're going to have to think, am I in degrees or radians? Okay. On your graphing calculator, notice that my calculator has radians darkened, shaded. That means I'm in radian mode right now. So I need to go down and tell it to be in degree mode. And the mode is right next to your second key. Okay? Now that I'm in degrees, you have a regular calculator, you want to make sure you're in a DEG or a D somewhere on your screen, not R or grad. DRG maybe. Yep. You want to make sure you're in D, not radian right now. Okay? Because our measure was 12 degrees, we need to make sure that we're in degrees. So once we are in degrees, we quit, and then we're going to take 3.5 and divide it by the sine of 12 degrees. And we get 16.8 feet. Is that a reasonable amount of feet for our ramp? Yes. Okay. So a quick check if you don't see, if your calculator doesn't show you on the face whether it's in degree or radians, is just to simply take the sine of 30 degrees. And you should see a half. 0.5. Questions on this one? All right, we keep moving. Now we want to use our calculator to evaluate the tangent of 37 degrees, 16 minutes, 37 seconds. Okay? So, do you remember that measure of that on your other notes, that 1 degree angle and how tiny that was? And on a paper it looked crazy tiny. I had to stretch it way out to make it look like an actual 1 degree, that you can actually see a measure of an angle. On our paper, it doesn't make a whole lot of sense to need 16 minutes, 37 seconds, right? But what if you're navigating across the globe? Could 1 degree cause a problem if you're 1 degree off? Absolutely. So what we have to do is break it down into minutes and seconds, okay, to be more accurate in both aerial navigation and also nautical navigation, okay? So when we're talking about the tangent of 37 degrees, 16 minutes, 37 seconds, how do I do that in our calculator? I don't see a degree, minute, second button on my calculator. Some of your scientifics might have it, but if it doesn't, what do you think we're going to do? How many minutes are there in 60, right? And how many seconds are there in a minute? Okay, so we have 37, and we need to add on 16 out of 60, and 37 out of 60 times 60, so 3,600. seconds in an hour. And 1 full rotation, 1 revolution of our clock. Make sense? Yeah, and it seems crazy on a piece of paper because it's so tiny, but when you think of a global scale, then it's pretty important that we have them. Okay, so we take 37 plus 16 over 60 plus 37 over 3600, we get 37.2769 for repeating. That's our decimal equivalent. Now we want to take the tangent of that. We're in degrees, we keep it in degree mode, right? We don't need to switch to radians. So we take the tangent of our answer and try it on your calculator to make sure you get the same thing I do. 0.761. That makes sense? All right, so we need to see the example, the next example with the secant. Okay, well, it wouldn't hurt, right? Secant doesn't, there's no secant button on our calculator. So same idea. We're taking 15 degrees plus 12 sixtieths plus 22 3,600. Okay, so 15 plus 12 over 60 plus 22 over 3,600, and we get 15.2061 repeating. You told me the secant is the reciprocal of which trig function? Cosine. Okay, so if we take the cosine of this number and then divide it by 1, or divide it into 1, we're good. We want 1 over this. So you can either do a 1 over cosine answer on your calculator, or you can take the cosine of this answer and then use your inverse button. Okay, so it's either 1 divided by cosine answer or cosine of your answer to that x negative 1 power. Find the reciprocal of it. Find the inverse of it. Everybody get 1.036? If you're doing it, following along on your calculator. Questions on this one? Feeling good? Okay. All right. So now we need to talk about sines, cosines, and tangents of special angles. We have those special angles that occur all the time, in building, in everywhere, architecture especially. And those are the 30s, 45s, and 60-degree angles. So if we start out with a 30-69, actually an equilateral triangle, and we drop a perpendicular from that vertex to the base, it splits it into two 30-degree angles, and it bisects the sides. So this was an equilateral triangle with 2 for each of the sides, and now the short leg is 1, hypotenuse is 2, and using Pythagorean's theorem, 4 squared, or 2 squared is 4, minus the 1 would get us 3, the square root of 3. So remember that? Okay, so we have sides that are in ratio of 1 square root of 3, 2, or 2 squares of 3, 4, or 16 squares of 3, 32. They all shrivel down to the same because they're proportional, they're similar. Always have those same ratios. So the sine of a 30-degree angle means start at the 30 and tell me what the opposite over the hypotenuse is. 1 over 2. That's why we get 1/2. the sine of 60 degrees is going to be opposite over hypotenuse again, square root of 3 over 2. Because sine and cosine are cofunctions, the cosine of 30 degrees is the adjacent over the hypotenuse, or the same as the sine of 60. And the cosine of 60 is the same as the sine of 30, because the adjacent over the hypotenuse is 1/2. I just kind of flip them, flip them, okay? And the tangent of 30, opposite over adjacent, right? So 1 over square root of 3, but we don't like to leave it as 1 over the square root of 3, square root of 3 over 3. I just remember that the tangent of 30 has all those 3's in it. And the tangent of 60 is I want the opposite over the adjacent, square root of 3 over 1. Okay? Now, the other special triangle that we have is an isosceles right. Two 45-degree angles, that means my legs are both the same. The angles are the same. Base angle theorem says that the sides opposite them are the same. That's the converse of it. So if this is a 45 and a 45, this was 1, this is also 1. 1 squared plus 1 squared, square root of 2. Okay, hypotenuse is the square root of 2. So when I want the sine of 45, doesn't matter which 45-degree angle you pick, sine of 45, we want the opposite over the hypotenuse. 1 over the square root of 2 is going to become radical 2 over 2. And sine and cosine are cofunctions, so 45 is 45 away, so yep, radical 2 over 2. And the tangent is going to be 1. So if you are a glutton for punishment like me, like I was in your seats, I didn't memorize these. I had to build the triangles and come up with them each time. Okay, you can do that. So think, yeah, it's just going to be a radical 3. Yep. Because if we flip the 3 over the square root of 3 and we rationalize it, we get 3 square roots of 3 over 3, and it just becomes the square root of 3. Yep. So far, so good? Now, let me show you the easy way, okay? Because I didn't memorize them, and there's an easier way. Square root of 1 over 2, right? Square root of 1 is 1. Square root of 2 over 2, square root of 3 over 2. And then just go backwards. Square root of 3 over 2, square root of 2 over 2, square root of 1 over 2. Okay, they're just cofunctions, so they're going to be the flip. So if you know how to count by square root of 1, square root of 2, square root of 3 over 2, you're in good shape this way. And then the tangent is nothing more than the sine over the cosine. If I took 1/2 and divided it by square root of 3 over 2, I get square root of 3 over 3. Square root of 3 over 3. Okay? Square root of 2 over square root of 2 over 2, 1. Square root of 3 over 2 divided by 1/2, square root of 3. So those can help you. There's shortcuts to memorizing these things. Okay? All right. So we talked about these already. Don't need to spend a lot of time. Reciprocal identities, the sine is 1 over the cosecant. Cosine is 1 over secant, tangent is 1 over cotangent, and vice versa. Make sense? Quotient identities, I just mentioned it. the tangent is the sine over the cosine. The cotangent then will be the cosine over the sine. Okay? Here's some new ones. These are called the Pythagorean identities, and I don't think you used them last year. So this is where I actually get to teach you something new. Okay? Sine squared plus cosine squared is equal to 1. If you memorize this one, you can derive the other ones. Okay? Because if I take sine squared plus cosine squared equals 1, and I divide everybody by the sine squared, one plus, what is cosine squared over sine squared? Cotangent, right? And what is 1 over sine squared? Cosecant squared. Make sense? That's where that one comes from. What do you think I can do to sine squared plus cosine squared equals 1 to make something else appear, or make another equation? How am I going to get this? Bless you. Divide everybody by guys are falling asleep. Warm in here. What am I going to do? This time I divided by sine squared. What do you think I should try to do next? Yeah, divide by cosine squared. Boom. What is sine squared over cosine squared? Tangent squared, right? Plus 1 is going to be, what's 1 over the cosine squared? Secant squared. Okay? So this comes into play when we want to show something like this. Those identities. How can we show that the secant of theta over the cosine of theta minus the tangent of theta over the cotangent of theta is equal to 1? I don't think it's equal to 1. It should be equal to, well, let's see. I have my slide wrong. So first of all, secant is what? Reciprocal of cosine. So 1 over cosine over cosine. It helps to put it over 1. What's that going to become? Well, when we multiply both sides by, or the top and bottom by 1 over cosine to make the bottom go away, right? Boom, boom. And we will get 1 over cosine squared, right? Okay. Tangent over cotangent. What's the cotangent equal to? Keep the right side the same. We want to work with the left side to get it to the right side. Okay? But 1 over tangent in the denominator, I flip, right? You just find the reciprocal. That's going to be tangent theta times tangent theta. What is tangent of theta times tangent of theta? Tangent of theta squared, right? And we just like to write it as tangent squared theta. What is 1 over cosine squared of theta? Cosecant. So the cosecant squared of theta minus the tangent squared of theta, isn't that one of our identities? Yeah. This is equal to 1, so 1 equals 1. We're done. Magic. Questions on this one? All right, last one. Show that that mess is equal to 2. As close as you come to proofs in pre-calculus. What do we do if we have a binomial and we're supposed to square it? Multiply it by itself, FOIL it out, right? Square the first term, multiply the two together and double them, and square the last one. Okay? I have to do the same thing to the second one, right? We're going to have to square it, so we're multiplying it by itself. Square the first, multiply these two together and double them. Square the last. When we square a negative, we get a positive. Let's combine some like terms. We have a positive 2 sine cosine. We have a negative 2 sine theta cosine theta. They disappear, right? They're 0. So now we have a sine squared of theta plus a cosine squared theta plus another sine squared theta plus another cosine squared theta equals 2. So you can do this two ways. You can say, I recognize this is 1 and this is 1. So 1 plus 1 is 2. Right? Or you could have gotten 2 of these sine squared thetas plus 2 of these cosine squared thetas and factor the 2 out. I think this is faster. Where? Right here? That's supposed to be a squared, yes. Apologies. Feeling good? Until this? Or not too bad. These aren't hard. It's a matter of getting used to them. All right, so assignment. Is on the calendar. 1 second.